5 kilogram mass on top. And here's a thought problem that's actually an applied problem, and I didn't even bring my pens down here with me, did I? Wow. So I'm going to raise the temperature. From 200 Kelvin to maybe 300 Kelvin. May not be enough to matter. Okay. This material here for now, let's assume that it's copper. You're going to have to tell me what the linear coefficient of expansion is, thermal expansion is for copper. I think it's in your textbook. If it's not, do a quick web search. I don't even have my phone with me today. You just want the linear coefficient of thermal expansion.
Where would this table be, in the back?
No, it would probably be in chapter 18.
Chapter 18.
I might even have it, come to think. I don't think I put these numbers down there. I didn't, so I don't have a figure here.
Copper.
Copper, 16.6.
These are specific heats from
16.6. Times 10 to the negative 6 meters.
Well, now you're not going to put that there. Then. So alpha is 16.6 times 10 to the negative 6 in the units.
Is M over MK.
Meters over meter
Meters
times
over,
Kelvin.
Meters over millikelvin.
Millikelvin.
Mucked up unit. Okay, this is. Now, what's wrong with this picture? Should not have a unit of. It should be in units of inverse.
It's meter per meter Kelvin.
Oh, it is meter
Yeah.
per meter Kelvin.
Meter per meter.
Gee, that's.
Yeah.
Okay, so basically it's inverse Kelvin because the meters cancel out. I don't know why they're showing it that way.
What's your subscript?
Cu, just copper. And if this were iodine cupride, it would be ICU. So what happens when I try to clean up my jokes? They come out horrible. Okay, so we have a thermal coefficient of linear expansion, okay? Now, by the way, the requirement for this to happen, just filling in the gaps, is that it has to have gained a certain amount of heat. Fair enough? If it doesn't gain a certain amount of heat, it's not going to warm up. Right? In order to warm up, it's got to gain energy somehow. Usually it's through thermal heat and thermal transfer. So, simple question first of all. What is the change in the length? Pretty straightforward calculation, so I'm not, I don't think, stretching you very much mathematically to solve this, but the change in length would be related to the initial length, or in this case, 1 meter, times the alpha, so 16.6 times 10 to the negative 6 inverse Kelvin, times a temperature change of 100 Kelvin. And by the way, the direction of the temperature change matters. Temperature change is always final minus initial. How much has something changed? How much is it different now than it used to be? It can be positive or it can be negative. If it's negative, it's a compression or a contraction. If it's positive, it's an expansion because it's gaining energy, gaining motion. So, oh my gosh, I should have picked a different number than 1 meter. Oh, so what's I give this? 16.6 times 10 to the negative fourth, or 1.6 times 10 to the negative third? Okay, and the units would be meters. So that would be delta L. How much work does this system do as it warms up? Well, let me say it this way. What happens if this is the ground and you got a heat source down below, what direction is it going to expand? Upward. Some amount. Don't know how much? Well, we just calculated how much. But it's going to expand. It's also going to expand outward, but it's going to expand a certain amount. Fair enough? There's 5 kilograms on top of it. So what happens to the 5 kilogram mass during this process? It moves up, not very damn much, but it moves up 1.66 millimeters. We'll just think about it that way. The work associated with this expansion, and that's what it is, it's work associated with thermal expansion. In this case, the work, and by the way, this is by the copper. Network is 0, right? We can hopefully appreciate that the network is 0.
Yes.
Constant velocity, so it's not accelerating. It's going to stop at the top. So the work associated with the copper on this plot would be the force, and in this case, the force is mg, right? And by that, force is mg. It's got to be mg. Times delta y. And delta y is delta L. So the work then should be equal to the 5 kilograms times 9.8 meters per second squared times 1.66 times 10 to the negative third. Guess the answer would be not very damn much.
Right. Right.
Something anyway, so 50.
0.08.
So it's about 8 times 10 to the negative something. 10 to the negative 2.
Yep.
Was it 8.6 or was it actually 8?
Or 8.134.
So, how much energy, how much Q, what is Q? We can't get a value for Q, but we can make some limitations on Q. What is Q? Or what is, say it this way, what is the minimum?
FMV squared.
too straightforward answer, actually.
Should be that, right?
It should be, it has to be at least equal to 8.1 times 10 to the negative 2 joules. Now, is that likely to be all the energy?
To lift the mass that distance specifically though.
Yes, for this particular distance. Now we say to lift the mass, delta y. This, so we have the right information. Has to be at least that. But clearly that's not it. Can't be all of it. There's a temperature change. So, let me ask you another question. How does the energy, the internal energy of the copper compare to what it was at 200 Kelvin when it's at 300 Kelvin?
It's higher.
How much higher?
Molecules are moving faster. Use a 1/2 mv squared.
Assuming that the mass itself doesn't gain any energy and no energy is radiated out. But what is the fractional increase in internal energy? What do we know about internal energy?
It's kinetic.
Now to think about this, now it's more of a thought problem in a sense. The total internal energy is going to be related to the average internal energy of one particle times the number of particles inside. Reasonable? Because each one is going to gain a certain amount of energy based on how much, or is going to have a certain amount of internal energy, and you add them all up. So the ratio, not the delta, so the ratio of internal energy final to internal energy initial going to be equal to the number of particles times the average internal energy at the end of the process divided by the number of particles times the average internal energy at the beginning of the process. I hope you see where I'm going with this.
I think the number of particles can cancel out.
You betcha. The average internal energy is proportional to temperature in Kelvin. So if I know the ratio of the Kelvin temperatures, at least I know fractionally how much more energy it has. So it's 1.5. In other words, by the time this thing has expanded, it's gained 50% more internal energy than it had before. So hypothetically, if this thing had an internal energy of 100 joules, not saying it had that, by the time it warmed up, it now has 150 joules. It's gained 50 joules, which means the total amount of energy that would have had to have been absorbed would have been 50 joules plus this number. You see that? So let's now extend this. How do we figure out how much energy was absorbed that corresponds to the temperature change? When temperature rises, it's because heat is absorbed. And there's a directly proportional relationship between temperature change and heat. So let's maybe make a statement on that because we're going to trying to put a puzzle here together for you. So, energy. I should put numbers on these, okay? So, this was A, this was B, this was C. I erased D, and this is E. All of this is just physical. Nothing fancy here. It's purely based on what we've been doing, even though it doesn't always seem obvious. So how much energy is necessary, or if you will, associated with raising the temperature? Okay? That's the idea. And it turns out that this was actually worked out before we even understood heat to be a form of energy. There was a time when we thought heat was an invisible fluid, kind of like the ether. And what we knew is when you warmed something up, it absorbed heat. We gave it another name, we called it caloric. And when it cooled down, it released this caloric. How do you know? Because you can feel it coming off. You know it's there. That's about the only way you can tell, though. It turned out a guy by the name of Joseph Black measured relationships between what he called this caloric and temperature change. Now, he did it in a relatively complicated way, but ultimately what he ended up coming out with was if you take a system that has a certain amount of mass, if you measure the temperature change that that system undergoes, the product of mass of the system, more mass means more particles that have to gain energy. Temperature change meaning changes in average energy per particle. But if you look at that product, it's directly proportional to the amount of heat that's been absorbed. In other words, it takes a certain amount of Q to raise a certain temperature and a certain mass. The physical constant that ties mass, temperature change, and heat together is called the specific heat capacitor. Or capacitor. I'm talking surface Latin class. Capacity. So now we have another temperature-dependent, we won't deal with it being a temperature-dependent property, but a temperature-dependent intrinsic property that's unique for different substances. It takes more energy to warm up water than it does to warm up the pan, pound for pound. So this quantity, which we call C, is referred to as a specific heat capacity. And what it is it's the energy per unit kilogram per Kelvin temperature change. So you may have seen that in chemistry or not, I'm not sure. But bottom line is that if you look at this as a number, if this number is 500, it means it would require 500 joules of energy to raise 1 kilogram of mass, 1 Kelvin unit temperature. So that's what C is. So if we want to know how much energy was necessary to raise this copper broth, we've got to do two things. First of all, we know what the temperature change is. That's 100 Kelvin. Better know something about the mass. I have no idea what the mass of this thing is, so I'm going to have to put a value in here. How about we calculate this? I like thought problems off the top of my head. So let's
What's the radius on a cylinder?
let's get a radius and let's get a density, and we'll figure out what the mass is. What's the density of copper, by the way? Look it up.
Oh,
It's about
off the top of
7.
my head,
You don't know? It's about 750 kilograms per cubic meter. Give or take, it's around 750. Okay? And let's give this thing a radius, about keeping with the theory of simple. How about we give it a radius of 10 centimeters? So 0.1 meters. So it's not 700, it's about 7,500.
Why is this in grams per centimeter cubed?
And because those are easier measurements in the laboratory. We typically measure grams and cubic centimeters. Because a cubic meter is the area, this is about area under this table about 1.5 cubic meters. We're always dealing with millionths to thousandths of a cubic meter. So it's not very practical to use cubic meters intuitively. It works for a number, but it's hard to tell what that means. But cubic centimeters are about the size of a cube of sugar, or a crap dot, if you will. So, come on, lucky 7, Daddy needs a new pair of shoes. So you think about that, how many cubic centimeters? So it's easier to think in those terms. Okay, so the density of copper is about 7,500. There may be a better number. I'm going to just use 7,500. We don't need to use something else. So it's about 7,500 kilograms per cubic meter. We have a volume of copper equal to 2 times pi times the radius, not 2 times pi r squared, excuse me. It's got a surface area of pi r squared, and it's got a length of 1 meter. So again, these numbers are relatively clean. But the volume of copper is going to be, give or take, about 3.14 times 10 to the negative 2 cubic meters. Pick nice round numbers. Oh, 10 times 10, right? To the negative 2 cubic meters. Okay. Now, the mass corresponding to that,
Those two multiply together.
it's density times volume. So we take this number, multiply it by this number. 25 kilograms?
Or 235.5.
Maybe. What? I don't know, that seems kind of high.
Are you actually using pi?
Yeah.
Well, okay.
10 to the negative 2, 1, 2, 10 to the negative 3, so, or 10 to the positive 3, so 10 to the negative 1. Pretty sure it's 22.5.
Do you say my calculator is?
I'm saying you're entering it maybe oddly in your calculator, I don't know. Is it, I could be off too, so I'm not going to claim anything, but if I took 7,500 multiplied it by 0.0314, I get 235, so, okay. Oh, 10 to the 1, not 10 to the 1. Okay. Does this make sense? I think it does, because if I had a full block of copper under that table, it would weigh 7,500, maybe 10,000 kilograms. And I've got 1/100th of that. So it's going to be in the order of hundreds of kilograms. So yeah, it's about 500 pounds. That's pretty big. Not something you'd want to just be lifting for posterity. This is poor Nicole, and she's doing her curls with it. Okay, so that's a lot of mass there, right? So Q, and now we need to know what the specific heat capacity is. How much energy does it require to raise the temperature? I know one thing. I might even have a value here. Of course I don't. That'd be too easy. Basic conceptual information. Metals have heat capacities that are about 1/10 of water. Water has a huge heat capacity. So just as for reference, capacity for water is 4,186 joules per kilogram Kelvin temperature change. So most metals are at least 1/10 of this.
Copper is 385.
There you go, thank you, sir. Okay, good thing to remember, just kind of keep things straight. Metals have low heat capacities, makes it nice to use for cooking. When you stick an oven, when you stick a copper anything, aluminum, iron on a pan on a hot plate, doesn't take much energy to raise the pan's temperature up, which means all the energy that's being absorbed, most of it goes to the water as you raise the temperature. So it's more efficient than, say, using water to heat up a small amount of metal. So for copper, as per Gustav, it's about 386.
It's also right here
Got to give the
on
reference
page
for it.
525.
Okay. So Q then, to raise the temperature, would be 386 joules per Kelvin, or kilogram Kelvin, times a mass of 225, times the temperature change of 100. Million maybe? More than that. Times that is about a million? 100 million?
8,600,000.
Oh, 8 million. See, close to 10. Okay. 8 million what?
8.6 times 10 to the
There's some joules going on there. 10 to the 9?
I think it's 9. I've got 9 digits.
No, it's going to be 6 or 7.
I guess 7 digits.
So, now by the way, this number looks huge, but understand, in the big picture of things, this is about the amount of energy a person needs to eat in a day. Right? Think about it in terms of food. This is 5 Big Macs worth of energy. Okay, this is a log burned in the fireplace amount of energy. Maybe less. So, it's a huge number. Joules are small energy units. We haven't dealt with that. We've always used small lifting quantities over small distances, small accelerations. But yeah, it's really not that big in the scheme of things. Now, how much heat needs to be absorbed to do this thing? There's actually even more in the picture, but I'm just going to we'll use this as a close approximation. So, what is now, given this information, what is the minimum Q absorbed? By the copper. So Q has to be greater than the heat required to raise the temperature plus the heat associated with doing that work, if you will, or W.